It can do it for you with a completion-only collator. Gradient accumulation, mixed precision, distributed training across many GPUs, logging, checkpointing, and the learning rate schedule, all built in through config. In the manual loop, you write each of those yourself. The interview insight is simple: know both levels. The from-scratch loop proves you understand it. The library proves you can use it. Another insider note: the notebook surfaces. Lora and its quantized cousin Qlora are the standard way to fine-tune efficiently. Instead of updating all the weights, you freeze the base model and train tiny low-rank update matrices, cutting trainable parameters by 100 to 1,000-fold. Full fine-tuning is for the final production run. Lora is for rapid experimentation. And there is a serving payoff Frontier Labs love. You can run many fine-tuned variants from one base model by swapping just the small adapter weights. Newer methods like Dora and stabilized Lora refine the training dynamics further. Now the satisfying part: seeing it work. The notebook keeps a frozen copy of the original GPT-2 and compares it against the fine-tuned one on the same instructions. Write a short poem, explain a neural network in one sentence, list a few benefits of exercise. The base model tends to ramble or just continue the prompt like internet text. The fine-tuned model actually tries to answer in the right shape. It is the same underlying network. The only thing that changed is that 1,000 examples taught it the interface. The notebook also adds a few rough quantitative metrics on held-out instructions the model never trained on. Things like average response length, how often it produces a non-empty answer, and whether it looks like it is actually attempting the task rather than echoing the format. These are crude heuristics, and the notebook is honest about that. They are enough to show the fine-tuned model behaving more like an assistant, but they are nowhere near a real evaluation, which is a thread we are about to pull on hard. So why does just 1,000 pairs change the model so much? Because the model already knows the content from pre-training. It saw plenty of questions and answers on the internet. SFT is not teaching it new knowledge. It is teaching it a new interface for accessing what it already has. People call this unlocking the model. The alpaca-style headers work because they echo patterns the model has seen: markdown headings, question and answer forums. And those format tokens become a switch that flips it into response mode. Now the failure modes, and this is where interviews live. The first is catastrophic forgetting. If you train too long, or with too high a learning rate, the model loses the general language ability it learned in pre-training. Large learning rates in particular shred the pre-trained representations in the early layers. This is the whole reason SFT uses such a low learning rate and so few epochs. You are trying to adjust behavior without overwriting the knowledge underneath. The second failure is distribution shift. You train on one mix of instructions and then deploy against a totally different one. If your data is mostly write a poem but your users mostly ask debug this code, quality quietly degrades on the things you never trained for. The fix is upstream. In the data, you want broad, diverse coverage of the kinds of requests real users will actually send, not a narrow slice that happens to be convenient to collect. The third failure is the subtle one: style mimicry. SFT can teach a model to sound helpful without actually being helpful. It learns the format and the confident tone of a good answer, the bullet points, the polite framing, and then produces plausible-sounding nonsense underneath. This is exactly why you need preference methods like RLHF or DPO on top of SFT. The slogan to carry into an interview is, SFT teaches the model what format to respond in. Preference training teaches it what quality to aim for. Let us place SFT in the full pipeline, a classic interview question. The order is pre-training, then supervised fine-tuning, then reward model training, then reinforcement learning with PPO. SFT is the step that produces the first instruction following model, The starting point everything downstream refines. And one nuance worth dropping: direct preference optimization is not reinforcement learning. It collapses the reward model and PPO stages into one supervised step on preference data. But SFT still comes first either way. The first big interview question is, how would you build a high-quality SFT dataset? The good answer walks the workflow: collect instruction response pairs, filter for quality, deduplicate, split into train and eval, and note that SFT sets are small, hundreds of thousands, not billions. The principal-level answer goes deeper. Design detailed annotation guidelines with rubrics, measure agreement between annotators with something like Cohen's kappa, adjudicate disagreements, and decontaminate against benchmarks so test answers never leak in. And name the real trade-off: diverse prompts with high-quality responses beat piles of near duplicates. The second money question is, Lora versus full fine-tuning. When do you use which? The good answer: Lora freezes the base and trains low-rank updates, slashing trainable parameters, so reach for it when compute is tight or you need many task-specific adapters, and use full fine-tuning when you want maximum quality. The principal answer adds nuance: full fine-tuning still wins on hard tasks, but Lora closes the gap as you raise the rank. Ranks in the dozens to low hundreds are typical for very large models, and methods like Dora narrow the gap further. And you can explain why Lora works. The weight update is approximately low rank. The production notes ground all of this in real numbers. Frontier SFT sets run from about 100,000 to 1 million expert-curated examples, deliberately not millions, because quality beats quantity. Expert-level annotations can cost tens of dollars each, so one round of data can run from the high hundreds of thousands into the millions of dollars. Training a very large model for SFT is a matter of hours on dozens to a couple hundred high-end GPUs, tiny next to the months of pre-training. And the recipe is steady: a few epochs, a low single-digit learning rate, an effective batch size in the hundreds. And the notebook is candid about the gap between this toy and reality. Real data is multi-turn conversation with system prompts and tool calls, and the masking gets fiddly. You mask per roll across many turns, and a single token offset can waste a run. Datasets evolve constantly, so tracking which data version made which model is a genuine engineering problem. You must decontaminate against every major benchmark with n-gram matching. And the hardest part is not training at all. It is evaluation, knowing when to stop and which checkpoint to ship, which is why teams lean on human eval and model as judge, not just the loss. If you read one paper here, make it Instruct GPT by Aoyang and colleagues, the blueprint for the whole pipeline. It lays out the 3 steps: supervised fine-tuning on human demonstrations, then a reward model on human comparisons, then PPO against that reward model. The headline finding is striking. A 1.3 billion parameter aligned model was preferred by humans over the 175 billion parameter base GPT-3, so alignment training mattered more than raw scale. One detail that surprises people: they trained SFT for 16 epochs, far past benchmark overfitting, because human preference kept improving anyway. So here is what you can now do. You can explain what supervised fine-tuning is, why it uses the same loss as pre-training but on curated data, and why label masking is the detail that makes it work. You can write the training loop from scratch, reach for TRL when you need to ship, and reason about the failure modes: forgetting, distribution shift, and style mimicry. And you know where SFT sits before the reward model and PPO. That is the foundation the whole RLHF stack is built on. Follow along on the frontier path, where Moot studies the machine learning interview in the open.